Okay, Assalamualaikum and good morning. So today will be the first lecture for PHY4503, which is on special relativity and classical field theory. So let me just mention about what this course is all about. So essentially what we're going to have is essentially going to special relativity, but not in the context of what you have seen probably in modern physics, but it will be more mathematical. So one uses a much more mathematical language to actually describe special relativity. Okay, so that's essentially what the course is. And the classical field theory part is essentially to deal with electromagnetic fields. Okay, so we'll be able to describe more efficiently electromagnetic fields within the context of special relativity. So, okay, let me begin by telling you, I should have shared. Let me share the screen first. Okay, can you see this? Anyone? Say yes, please. Okay, great.
Yes.
Okay, thanks. So before we start, just to let you know the course assessment plan for this particular course. So there will be quiz and assignment. The quiz will be 5%, assignment 10%, test 1, test 2, 15% each. And there will be an SEL, which also takes up 15%. So the final will be 40%, making up to 100. Okay. I'm still not sure yet whether your assignment and SEL will be in group work, but I suppose at least SEL will have to be in group work because it's more in terms of text rather than equations. Okay, so assignment, let me decide later on. Okay, hopefully if the number is still small, then you can do it individually. Okay. SL, perhaps maybe a pair of you pairing up to look into some journal articles. And what are essentially the reference books? Well, I listed 5 here. It's not necessarily limited to this. The first one is probably the one main text, which I find similar to the notes that I have. Let me mention that my notes are essentially the ones that I actually learned during my undergraduate. Okay, but of course I've upgraded that, okay, to include more recent facts and more new things. So essentially what you're learning is just the same thing what I'm learning during my undergraduate years in Adelaide. Okay? So, but there will be some features added to make it a bit more modern, but really you can, because it's an old subject, it's last century, so there's not much new things that one can add without making it two at once. Right, so the first one, it will be a good one for you to look at. The others is probably, well, the second one is quite good. The third one and the fourth one is probably useful when you do field theory. the classical field theory. And then the fifth one is also quite thin, so the book itself is called Concise Course, so you can also look it up. Okay. Okay. Any questions with respect to this? Guess no. Okay. I've already uploaded the first two lectures. I'm doing this gradually just to see, okay, if I need to make amendments to the lectures or not. Okay. So here's the first one. Essentially, the first two lectures will probably, in fact, three lectures, will probably be something which is you're supposed to know it before you go to special relativity. It's from mechanics. Okay. I'm not sure how far you how far have you learned about reference frames inside classical mechanics, but these are going to be important in the context of special relativity, and hence before we go to that, we need to understand reference frames even in the context of classical mechanics. Excuse me. So, okay, now if there are any questions, okay, let's see who's coming in. If there are any questions, then you can simply, voice out, because I can't see you when I'm presenting. So we'll start with this. So essentially, we are going to look at the idea of how reference frames in mechanics, okay, and the general philosophy behind it. So the idea is essentially when you do physics, we normally think of the laws of physics to be universal. So it doesn't matter where the physical process is going to be. If it's on the Earth or on the satellite, then you expect the laws of physics to be the same. There might be some more exotic things happening in space, but meaning whatever laws of physics in this particular case is about space and time, then we claim that this must be universal in some context. Okay. Okay. The next statement is independent of context. Right. Let me just see who that is. Okay. So the idea is the laws being universal. That means it's supposed to be independent of context of measurement. Okay, so in other words, where you do the measurement, where you actually observe the phenomena, should not be what I call a factor in giving you that laws of physics. So again, the results of a particular experiment, of course, it will have to depend on the observer's position, the specification of the observer. Okay, and this is normally with respect to the position in space and time. So one has to always remember when you see a physical result, there is a reference frames coming in. So where the observer is actually doing the measurement or doing the what you call observing of the phenomena. So you need to have this concept of reference frames that will be an integral part, but sometimes we just ignore it for our convenience. But you know that there's a what you call reference frames that we are attached to or used. Okay. So with respect to the reference frames themselves, we often build up what we call coordinate systems. Maybe I should start using so that Okay, so this is the coordinate systems that we often use. So once you use a coordinate system, then you can actually locate a particular position. Besides that, you can once you are able to locate the position in space and time, one can do calculation with those. And because this is tied up with the reference frame, where is it? Then it's not going to be unique. Okay, so it's not going to be unique. Sometimes even within the same reference frames, an observer can use two different coordinate systems. Okay, so that means there's a freedom of choice what coordinates that one can actually use. But even greater is the fact that if you have different reference frames, then you will certainly have different coordinate systems. So one needs to take that into account when you do comparison of experimental results or comparison of calculations. So the reference frames themselves are usually made by normally when we do the observation, sometimes the observation is for particular system, for physical system, and we consider ourselves observing that physical system external to the system. So, but then where we actually observe it then will depend on the reference frame. Okay, so there's that reference frame which is external to the physical system, or sometimes is attached to the physical system itself, meaning the observer is within the physical system. So you have these two possibilities that one needs to take into account. So usually when we talk about, for example, external to the physical system means we look at a laboratory frame. So you are actually you set up the coordinates for laboratory. Okay, so you are external to that laboratory. Okay, so and the frame themselves can be stationary or moving. Okay, so this is probably known to you. For example, when you have when you do physics on in a moving car, you might see some deviations from the normal physical laws. Okay, particularly when it's accelerating. Okay, so these are things that we need to also be aware of, whether it's stationary or it's moving. Okay, and quantities associated to this phenomena may be different in the sense that you may have deviations from the laws that you see, say when you do the experiments in a lead frame, okay, where you consider it's at rest, and when it's actually moving. So these are things that we have to be aware of when you do special relativity or in general physics. Okay. So one of the things that we have mentioned before, the physical laws themselves must have a sense of universality. Okay. So in other words, this universality, how can we get this when everything you do depends on the coordinate systems of the reference frame? That means there must be some nature of the quantities that you're describing, okay, are going to be fixed in some way or another. Okay, so and normally we call this characteristic being geometric in nature. Here's a cartoon showing you a particular phenomena given by this particular vector. Okay, so and then this vector will if you use the ordinary vector algebra kind of thing. You have components to it. So it really depends on the reference frames of the observer, how these components of this particular vector is going to be. Okay, so another observer will have a different set of components of the vector, but both can be made to agree that this vector is pointing in space in some direction. Okay, so that is the geometric character, meaning observer A, for example, over here, and observer B may have different components for V, but they can actually communicate their results to each other, and they still can manage to say that, okay, it's pointing in the same direction. Okay. So how do they do this? Normally, they have what we call the transformation laws. So over here, observer B might have some components, and observer A might have some components for the vector V. There will be some transformation laws for the components of the vector itself. Okay, so this we will learn this in probably in a few sections later. Okay, so once you have these transformation laws, then the different observers can communicate their calculations or their measurements, for example, and then they can compare their results with each other using these transformation laws. The fact that you have this transformation law is actually a kind of a physical principle in physics, and it's called covariance principle. Okay, so in other words, there must be something that connect one set of measurement to another made in different reference frame. Okay, so you will behave in some orderly manner where you can actually make the calculations to convert from one to the other. Okay, right. So this is very much philosophical at this stage. You'll see later on there will be a lot of calculations. So the ability to transform from one frame to another is essentially saying that, okay, the two different frames, for example, for observer A and observer B, they are actually equivalent, because they can make to agree that a particular vector is pointing in some direction. Okay, so when it's equivalent, but they might have different descriptions, that is essentially the idea of relativity over there. Okay, the descriptions can be different, but they can agree they can agree that it's the same physical phenomenon. The same physical phenomenon has been observed. Okay, so the ability jumping from one frame to another and then back and then to other different frames is essentially the idea of relativity. Okay, so let's go to enough of that philosophy in some sense. Let's go to mechanics, where you have learned this from Tadika. I suppose you learn about mechanics all the way through until university. And we can recall the three laws of Newtonian mechanics. The first law being effectively saying that free particles move with constant velocities. And then the second law is essentially F equals ma, which says that, okay, if there's a presence of a force, then the particle will essentially accelerate. Okay, and the main thing that one needs to observe here, these are actually vectors. Okay, and you remember the description of vectors can be different in different reference frames, so you need to understand that. Okay, And then the third law is essentially the action and reaction equal in magnitude and act in opposite directions. And this is also interesting thing because you can attach a frame on one, and then the reacting body will also have another frame, and you can describe the physics that happens between them and in a what we say covariant way. So that means you can actually make a transformation from one frame to the other. Okay. Any questions so far? I think it's pretty philosophical at this stage. Just shout because I can't see you. Right. The kind of reference frame that we normally attach to a mechanical system is what we call a rigid reference frame. So why this is actually important? Because it allows you to faithfully describe rigid bodies. So if it's rigid in one frame, then it should be also rigid in another frame. You will see that this fact is going to change a little, okay, in the context of special relativity. So your reference frame in relativity is not really observing this rigidity, okay. So the reference frame, the points of the rigid bodies will be coordinatized by, say, spatial coordinates and also the time, okay, when you do the particular observation or measurement. And we call this R and T, okay, as the coordinates of an event. Okay, this is going to be relevant. Usually when you do magnets, you might not think about time too much. Okay, you just coordinate your event just using this what you call spatial coordinates, because you know your time is like a kind of a background coordinate kind of thing. Okay. So, but in context of relativity, it's important to have this notion of an event. Okay. Right. So here's a description of vector. So we'll try to be a bit more specific now. Vector is given by components, for example. Okay, and when you have components, essentially this is with respect to projection to some reference frames. So there will be unit vectors, the basis vectors EI over here. So generally I put this as an the symbol EI because I can describe in any coordinates, but you can think of your EI to be your IJK. Okay, so you have 3 of those, and then you have the components which projection along X, Y, and Z as an example. Okay, so this is essentially the components here. Okay, and even if you use your Cartesian basis, in this case, this is what we call a Cartesian basis. It's sometimes useful to write them as this E's with a number instead of your IJK, because we are going to use what we call the Einstein Summation Convention. This is just a shorthand notation, okay. So as you can see, when you do the expression of this particular vector, there's a sum, okay, and then this I over here correspond to this I over here, saying that this component correspond to this particular direction, okay. So what we're going to do is, because you have this feature most of the time, Einstein made this summation convention, saying that, okay, I can, since I have this index being repeated, I can actually ignore them and think of them as a shorthand notation for a sum. Okay, so here one can actually think this being sum over I 1, 2, 3. Okay, so if there are more dimensions later on, for example in space-time there will be 4, then this will be sum over 4, for example. Okay, but in this context it's just 3 because we are discussing mechanics. Okay, so the repeated index means summed, and it's sometimes called the dummy index because you can replace this index by a different symbol. So for example, VIEI, it means the same to have VJEJ. This means also a sum. Okay. So in other words, repeated index can be replaced by different symbol like V bar, E bar, for example, if you want. Okay, I'm just saying that that index is just replaceable. Okay, and one can use different symbols to mean the same thing. Okay, so but there's a condition. There's a condition that the index that being repeated can only be repeated twice in any particular term. Okay, suppose I have many terms. For example, V equals to V. Let's make this. Okay, I'm going to make it. Okay, maybe I use a different symbol. Let's say I say R. Okay, so I'm going to say that R is given by U I V I plus V J W J. Okay, and you can see over here in one, this is what we call one term. Okay, so in one term your index can only appear twice, the same index. Okay, and if you have, for example, two terms like this, you can repeat it if you want to, because they appear on different terms. So this is still considered valid, okay, because it's repeated in a different term. But within one term, for example, let's do something like this, UI, VI, WI. What's the problem with this? Okay, so here I have this repeated index and this repeated index. So which one I'm going to sum over with? Okay, so you have this ambiguity that we want to avoid. So in other words, this thing should not happen. Okay. Right. Any questions so far? I think that's pretty obvious. I think I did also. If you took mathematical methods under me, I probably have also introduced this summation convention before. Okay. Okay. Another sloppy thing that we are going to do, because sometimes we don't want to say too many things in a sentence. Okay, sometimes we just refer to the index object over here, VI for example, as the vectors themselves. Strictly speaking, VI is the components. Okay, but if we see a single index object, then we can actually immediately identify that to be a vector. So these are things that we're going to assume, no, not all the time, but no, on and off. Okay. And then the other thing about basis vectors, Okay, this goes back to, okay, when you have reference frames, you can coordinatize it with different coordinates. Okay, association of reference frames. The normal context you use an orthogonal coordinates. One can also use a non-orthogonal coordinates, meaning the axes might not be orthogonal to each other. Okay, so for us, we are more no, we are going to adopt just the orthogonal coordinates for now. If you're doing something much more exotic like general relativity, which involves warping of space and time, you might want to allow for the use of non-orthogonal coordinates. Excuse me for a while. Okay, sorry about that. Right. So for the case of the orthogonal coordinates, your basis vector is going to be behaving in this manner. When you take the dot product between the two basis vector, it either gives you 1, and this happens when I equals to j. So E1 dot E1 means I dot I, for example, is 1. But if I is not equals to j, like I dot j, E1 dot E2, then that will be 0 because it's orthogonal. Okay. So in this particular case, this will help simplify a lot because we can introduce this symbol called chronicle delta that represent this 1 or 0 cases. Okay. And this chronicle delta later on will be a particular geometric object that we're going to mention in a few minutes. Okay. The chronicle delta, as you see over here, written here, can be acting like what you call an index lowering operator. So you remember that our vector that has been introduced so far has the index on top. The basis vector on the other hand is actually with the index at the bottom. Okay, it's just a convention at this particular stage. Okay, so if I were to write this delta ij together with this vj, remember our index summation convention. Oh, did I mention that before? Let me just check if I've written that. Oh, I didn't say it out, but it's written over here. Any free index should be conserved on both sides of the equation. Okay, so in this particular case, I have j being sum on the right hand side, so it's a dummy index, so it doesn't matter what this symbol is supposed to be. Okay, but I have an index I. This is what we call a free index. It's not being summed. Okay, so that free index should also appear on the other side, the left hand side. So this is a free index. So what is happening here? Well, as I mentioned, our vectors so far will have the component with index on top. Now you have a new object with the index at the bottom. Now my claim at this stage is this new object with the index at the bottom is actually corresponding to a dual vector. Okay, the original vector has component vi here, with index on top. The dual vector will have vi index at the bottom. Okay, and we're going to call these vectors differently. the index at the bottom is called a covariant vector, and the vector with the index on top is called a contravariant vector. Now, what do they mean? We'll see later on. Okay. So the covariant vector is said to be dual to the contravariant vector. If you have done quantum mechanics, for example, you know what dual vector to a ket vector, right? So it's more or less the same kind of thing. So in other words, your ket vector is like your contravariant vector. Your bra vector is like your covariant vector. Okay. Now you might ask, in that context, it's quite clear what's the difference. But you might ask, in this particular case, what's the difference between these two? Well, we will see later on that they are just the same. Okay. Now what happens is that your delta ij, you can think like, if you have a matrix M, you remember if I introduce index notation for matrices. So here's a matrix M. I want to specify the ijth element. I just put this subscript ij at the bottom, right? So your delta ij is more or less the same kind of thing. Okay. Your delta ij is, in other words, is, if you look at how the Kronecker delta being defined, this delta ij are just your matrix elements of the identity. Okay. So when I equals to j, it will give you all this 1. When I is not equals to j, it will give you all these zeros. So in other words, delta ij can be identified with the identity. Okay. So in other words, I can think of the following, where Vi equals to delta ij Vj from the equation earlier. This is just like acting the identity matrix to Vj. Okay. So in other words, if I want to write in terms of coordinates like x, y, and z, Vx at the bottom is equals to Vx with at the top, okay, and the same for the rest. So you might ask, why bother with the ordering of index on top or at the bottom? Well, later on you'll see that your covariant and contravariant vectors in special relativity will be different. It's just in the context of this classical mechanics, they are just the same thing. Okay. Right. So we have mentioned just now, your delta ij acts as an index lowering operator. Here's another particular case over here, delta ik, ak, j. So I'm just using the index notation rules. K and k here is a dummy. Okay. So in the equation that doesn't mean too much. Okay. But your free index means something. Okay. So the free index, you have to remember that it must conserve on both sides of the equation. So in other words, whatever this object that multiplies with this Kronecker delta is, the index ij will also appear on that object. Okay, so here it means that, okay, I'm going to have a new object called A. Well, I mean, it's the same thing, same A actually, but never mind. Aij with the index both at the bottom. Okay, so that's just a different example from the earlier example before. Okay. The other thing that one needs to know is this delta ij is, if you look at the definition, remember, 1 if I equals to j, 0 if I is not equals to j, then this also works for delta ji. So in other words,
your delta ij is what we call a symmetric object. So you can swap the order of this index on the object. And what else one can have with delta ij? Well, delta ij can implement what we call the dot product. Okay, so how do we do this? Okay, we think of your v dot v. So if you think of what v dot v in this particular case would be vi, right? Okay, let's say vx plus vy plus vz. Okay, how can this work now? Essentially, okay, so far we have seen that the summation only works with respect to a sum between index at the bottom with the index at the top. So this is in some way it's like an illegal thing to do, but we can make it legal, so to speak, by introducing this Kronecker delta. Okay, so I can think of this as a sum, okay, between I and I here and j here, and if I lower this index, this becomes vi, and if I lower the index on I here, then this becomes vj. And what does that give you? That gives you the length squared of your vector. Okay. So in other words, something that gives you a description of a length is sometimes called, well, it's not sometimes, it's called a metric. Okay. So your delta ij somehow implements what we call a metric. A metric is essentially something, it takes an object in a particular space and it gives you some number. Okay, sometimes it's called a distance function. Okay, so your delta ij is sometimes called the Euclidean metric tensor. Okay, because why? It gives you the concept of length. Okay, by contracting this what you call the components of the vector to give you a length square. Okay, and the space that has this Kronecker delta, so a space, in what sense that would be a space with, say, orthogonal basis. Okay, so any orthogonal basis can give you this particular space, okay, and this is called a Euclidean space. Okay, I hope that's clear, everyone. I hope you're still there. Any questions so far?
Could you repeat the explanation for number 3? I don't really get it.
Okay. What I'm trying to say is, if you remember what's a dot product, maybe I'll go to this whiteboard here. A dot product in the usual sense is just this thing. Okay. So I'm going to be consistent here. I'm going to write Vx plus Vy plus Vz. Okay, this is your V1 plus V2 plus V3, right?
Yes, doctor.
Okay, but so far our summation, so this is a sum, right? It sums our V1, V2, V3. So far our sum has been introduced in a way that, okay, I'm going to contract Vi, say Wi. One index on top, one index at the bottom. So that's the rule that we have introduced so far.
Okay, in some ways it doesn't matter in the case of the Euclidean space, but this rule is going to be important when you do special relativity. Okay, the index summation is usually uh, uh, have the index 1 on top and 1 at the bottom. So in order to make this looks like uh, uh, this kind of thing, you remember that, okay, for Euclidean space, Vi is just the same as Vi. So I can rewrite this as what? V1, oops, seems to be, oh dear, don't hang. You still seeing this?
It's a
Still here, right? Okay, can you see?
whiteboard, yeah.
Okay, so I can now what you call since Vi equals to Vi at the bottom is equals to Vi at the top. Okay, I can rewrite this. There's no problem with that. So I want a 1, not I. 1 plus V2 plus V3. Right? No problem with that because I know that happens in the case of the Euclidean space. And this is essentially what? I mean, this is Vi, but what I'm trying to say here, how do you get this Vi? You do the following. Vj delta Ji Vi. So this gives you Vi. So is that right? So it's not so this idea of index on top and at the bottom is not important here. Okay, but as I said, later on when we do special relativity, it will make a difference. Okay. So so let me go back to the notes. I think I want to finish this thing off. Maybe they will not get to finish it. So the idea now, remember this idea of what you call vectors being indexed is fine. Okay, you know that there's a component to each vector, but the important thing is now can you compare vectors in different reference frames? Okay, so you can. What do you do when you do reference frames? You normally fix a coordinate system, right? And then when you change frame, you have another coordinate system. Okay, so the other coordinate system will have bases, and the original coordinate system will also have bases. So there must be a relationship between these two coordinate systems. And if you want to preserve orthogonality, for example, then the kind of transformation between one basis to the other, it has to be linear. So a linear transformation is given by this. So I cannot have something like a square kind of thing. Okay, it can only be linear. Or I cannot add something like this, for example, plus a constant kind of thing. That's not allowed. Okay, so it has to be a linear transformation, and I think you have done linear transformation before, right? In maths method. So this is a linear transformation. So here is the index over here is the dummy index over here is I, and then this being sum, and then you have this free index J dash. So you convert from a basis in the dash. Let me just say that this is a basis in dash frame. To another basis in undash frame. Okay? So remember, we need to compare reference frames, right? So the way to do it is we look at the basis first. Okay? Once you look at the basis and we know how it transforms from one to the other, okay, let me spoil the story a little bit. How do you can change the basis in a way where you can rotate it, right? So in other words, this will be a rotation matrix. Okay. So now, okay, we are not, okay, once we know how to do the, with respect to the basis, then we should be able to know what happens to the vectors in general. Okay. So a vector V in one reference frame, how does it connect with a V in the other reference frame? But you have to remember, your V is pointing in one particular direction in space. So as a geometric object, that direction doesn't change. The one that changes are essentially your components. Okay, so in other words, if you compare the components over here, so I'm writing in terms of undash frame here and a dash frame here, you'll see that, okay, because I know how to transform the basis, I'll be able to make the connection between this component with these components. So what do? I know what Ej dash is according to this equation. Substitute that equation in, then I'll be able to say, okay, I will get this. Okay? And if we look at over here, this is EI, this is EI. Right? So you make the comparison between the two, then I'll be able to say that, okay, the components of the vector will transform in this manner. Okay? I have 5 minutes left. Let me see. Okay, we can do, here I'm using this equation, right? Let's suppose I do an inverse transformation. That means I'm connecting, here I'm connecting this undashed basis to the dash basis. So the inverse transformation is to do a reverse. Okay, you connect the dash basis to the undashed basis. So this will be the inverse transformation. So again, doing the same trick, then you'll find that, okay, in this particular case here, okay, I'm just making this different at the moment. Okay, here I'm labeling this transformation matrix over here with A. Here I'm labeling your transformation matrix over here by A tilde to show that it's a different matrix. Okay, so then you'll be able to see that the components of the vectors will change according to this inverse transformation. And so here you can compare with that above. Okay, here using this matrix Aij dash, the dummy index is J dash. Here the dummy index is your I. Okay. If you like, we can always write this as a matrix equation. As I mentioned, it's supposed to be a matrix anyway. So this would be this one here, and this one corresponds to that. So this A tilde is this matrix, and this A is this matrix. They are supposed to be different matrices.
But you'll see later on that maybe in the next lecture that A tilde and A should give you the identity because they are inverse to each other. And in fact, your A tilde is essentially equals to A transpose. So what does that say? That says that A transpose A equals to I, which is essentially the property of orthogonal matrix. Okay, what's an orthogonal matrix? Well, a rotation matrix is an orthogonal matrix, and a reflection matrix is an orthogonal matrix. So I'll stop there for today and we'll continue this in the next lecture. Are there any immediate questions? Otherwise, I will stop. Let me take your attendance first.
The
Yeah?
my
Yes?
friend beside me, kita orang kongsi satu laptop.
Compare?
Dia tak masuk dalam Google Meet ni.
So, okay, never mind. You just let me know who the person is later on. Okay?
Okay.
Right, so I'll stop there for today. So thank you everyone. The next lecture will be when? Tomorrow, right? Tomorrow, Thursday at 9. Okay.
Tomorrow.
Okay, thank you everyone. So I'll finish off today. Thank you.
Thank you, Doctor.
Thank you.